A bad picture hanging job uses three wires. The first makes a 30-degree angle from the ceiling, the second hangs straight down, and the third makes a 50-degree angle from the ceiling. If the tension on each wire is 22, 45, and 17 newtons respectively, what is the mass of the picture? So we're looking at something that's rather like this. You have a picture that has three wires that are supporting it. The first one makes an angle of 30 degrees from the ceiling. The second one is straight down, and the third one makes an angle of 50 degrees. The vertical components of all three of these vectors will have to support the weight of the picture. So each of these three will contribute to a force that is going to balance the picture. The vertical component of the one on the left, if this is 30 degrees, then this is also 30 degrees. The vertical component is going to be 22 sine of 30 degrees. The one in the middle is vertical, so it's contributing all 45 newtons of its tension. The one on the right is hanging 50 degrees, and so the vertical component here is going to be 17 sine of 50 degrees. The three of these forces added together will give us the magnitude of the force that is supporting the wire. So we have 22 sine of 30 degrees always make sure your calculator is in degree mode when you're using degrees. So this is going to give us 11 newtons. This is 45 newtons. And this is giving us 13.0 newtons. If you add these up, you have a total of 69 newtons for the vertical force of tension. So that's going to be equal in magnitude and opposite in direction to the weight. So we know that the weight is a negative 69 newtons, which is equal to mg. G is a negative 9.81. So we know that the mass is going to be equal to approximately 7 kilograms. Now, an interesting thing about this particular problem is ideally the horizontal components should also cancel, so that in this case we have 22 cosine of 30 degrees and we have 17 cosine of 50 degrees. So those should be the same size and opposite in direction. .91, 19.1 newtons. And 10.9 newtons. So not quite right. It is in fact a bad hanging job for the picture. And you could calculate, since this is larger, it's going to accelerate to the left. You could actually calculate the acceleration of the picture now that you know the mass. So since the mass is 7 kilograms approximately, the force is 19.1 newtons. The mass is 7 kilograms, and so the acceleration to the left, the force is not 19, it's 19 minus 10.9, which is 8.1 newtons. So in fact, this picture should be accelerating at about 1.16 meters per second squared. I'm going to put a negative on that because it's to the left. As I said, it was a bad picture hanging job. Vlad has a mass of 65 kilograms. He slides down a highly polished 25-degree ramp. into the dungeon. What is the magnitude of his acceleration? So what we have is we have a ramp that's 25 degrees. We have Vlad, which I'm going to represent simply by a box because I do not draw well at all. And he is going to be experiencing a weight that is mg. He's 65 kilograms. And g, of course, is a negative 9.81. So the force straight down is going to be a negative 637.7 newtons approximately. So that is the force straight down. But we're used to dealing with normal forces and parallel forces. When I say parallel, I mean parallel to the surface. When we have something like this on a ramp, I typically label my forces as Fn for normal that we're used to, and then Fp for parallel, as in parallel to the surface. Okay, so what we actually will have here is a right triangle inside, this being the Fp, simply translated. The magnitude we know was a negative 637.7, and we have a normal and a parallel force component. Well, the 25-degree angle, if you play with the geometry a bit, essentially you can twist this triangle, this inner triangle around, is the same thing as this theta inside. So what we're looking at now is his acceleration. And in fact, we really did not even need to find the magnitude of the force. We could have simply worked from the same triangle looking at his acceleration. Is going to be Fp, which is your acceleration times the sine of your angle, negative 9.81 times the sine of 25 degrees. So in fact, he's going to accelerate down the ramp at about 1.15 meters per second squared. You could calculate the normal force as well, or in this case it would simply be the negative 637.7 times the cosine of theta, which would be approximately 578 newtons, but that's information beyond what we were asked. Kepler's laws of planetary motion. So Kepler, from good old empirical evidence of observation of planetary positions, was able to deduce 3 laws of planetary motion. The first law, planets move in ellipses. As opposed to a circle, which would be something like this, an ellipse is a much more